All right, welcome everybody to our Wednesday afternoon RAL seminar after your lunch. Thank you to all of you for being here in person and many people online as well. And it's my pleasure to introduce today our speaker who is visiting here on a long-term basis from the University of Bologna in Italy. He's been working with Stefano, Alice, and Jeannie and myself. And he'll talk about some of that research today. He's a PhD candidate at the University of Bologna. And a piece of trivia, some of you may know, but this is the oldest continuously running university in the world. It was actually founded as a place of teaching in the year 1088, so very impressive. He's studying in the Department of Physics and Atmospheric Science under Professor Silvana Sabatino, and again, has been visiting NCAR since mid-January. Came straight here after the AMS annual meeting. A little going further back, he obtained his master's degree in the physics of the Earth system at the same university in 2022. And before that, got his bachelor's degree in physics at the University of Trieste in 2020. So very impressively, he has already 5 publications in print on a variety of topic and convective storms, including windstorms, hail outflows, and tornadoes. And I believe he has the most number of publications on severe weather in the Po Valley in Italy, and has more publications on the way. He's been given a number of awards for his conference talks, including the Young Scientist Conference Award at the European Meteorological Society, and a variety of other awards, and has founded a number of organizations in Italy related to severe weather, including this pre-temp, which includes students and meteorologists that's aimed at improving severe weather forecasting in Italy, and includes collaborations with the European Severe Storms Lab, Meteo Network, and a variety of regional environmental agencies. In his free time, he's been taking advantage of Colorado. He loves the outdoors, climbing, running, hiking, and also storm chasing. In fact, he and I went together to the Northwest Oklahoma, just over a week ago. And we were really nervous when we saw about 5 tornadoes drop about 40 minutes from home, close here at DIA. So I thought he was going to dump me in the hail core. Thankfully, our storm ended up producing a show. Anyway, I'll stop talking and I'll hand it over to Francesco.
Thank you very much, Chris, for this very nice introduction. Too long, I think, too much things. It was not necessary. Thank you all of you to be here. It's a big honor for me to hold this seminar in this Temple of God for Gods for Atmospheric Sciences. So it's for a student from a pretty small country, you know, it's a bit quite exciting. So I would like to acknowledge my co-authors, so Chris, Stefano Alessandrini, Andrea Zonato, and Silvana Di Sabatino for helping me to carry out this research. And yeah, I divided my presentation in 5 main parts. I will start with an overview on the topic, so state of the art. Then I will present the numerical simulation setup and the investigation method. And then we will jump on the results. So first of all, discussing the supercell sensitivity to the urban morphological parameters, and then fourthly, the sensitivity of the pre-storm environment to the urban morphological parameters. And finally, I will sum up and with some final remarks. On the left, there is the beautiful tornado that I chased last Friday with Matt Wilson, and it was a very great chase. And okay, let's go. So state of the art of this regarding the broad topic of severe storms and urban areas. This topic has been studied since 1970s at least, so there is quite a lot of works, at least regarding moist convection and urban areas. And for example, this is a paper of Robert Bornstein and King-Lun Lin back in 1999. And this was an observational study in Atlanta where they found basically that convective storms can be initiated over urban areas because of some wind convergence and the presence of the urban H island. Then there was this work by Chris Rozoff and co-authors, and this was a numerical study where they tried to understand which phenomenon related to the urban land use is more important to create the storm. And the answer was that the urban energy flux was the most important effect related to the city to trigger a storm. So basically the urban island, this thermodynamical component. More recently, in 2024 was published this comprehensive work where they considered hundreds of cities around the world using satellite data, and they found a consistent, coherent intensification of precipitation downwind of cities, especially the more compact ones. This is regarding generally the topic of moist convection and urban areas, but what about severe storms? We know that for severe storms, there are three main ingredients that are necessary to produce or organize severe storms: the thermodynamic, the kinematics, and the trigger. So regarding the thermodynamics, we know that the urban land use can influence the temperature because of the urban island and also the moisture. So you can have less moisture in the city because there is less evapotranspiration. And then what about CAPE? Because CAPE is related both to temperature and moisture, so a priori it's not really clear what is the most important, if there is an intensification or decreasing of CAPE. Regarding the kinematics, we know that due to the drag over the city, the winds are reduced, and so we are expecting that also the wind shear is increased on the opposite side. But it's not clear if this intensification of wind shear is enough strong to modify your severe storm or not. So this is something that should be investigated. Regarding the trigger, maybe there is more consensus that there are some wind convergences induced by the city, and then we are expecting also some vertical velocities that can trigger the storms. Okay, regarding this, there are a few papers published in the last years. For example, there was this one by Larissa Reims and David Stensrud back in 2018. They used basically an ensemble approach trying to understand if a supercell, the simulated supercell, was sensitive to the position of the city in the numerical domain, in the simulation domain. And the answer was yes. Changing the location of the city, they observed a modification of the storm behavior. Last year was published this work where they were using CM1 in this case, and the city was parameterized as a bubble with higher temperature and roughness. And they found, in this case, a significant intensification of the low-level mesocyclone. So this is a very brief introduction, the state of the art of what was done so far. And now I'm going to present you the numerical simulation setup and the investigation method that we used in the last few months. So I'm using WRF at 1K of resolution. I'm using as boundary layer scheme YSU. I have the radiation in my simulations. I'm doing idealized simulations. Okay, maybe I didn't say that, but I'm doing idealized simulations. And I'm using radiation because we need the radiation to develop the urban island to create the urban circulation. I'm using periodic boundary conditions. The simulation is initialized at 10 a.m. in the morning, and the storm is triggered at 4 p.m. with a thermal bubble. I was forgetting to say that, I'm using the radiation. The radiation is the one of May 31st at a latitude of 45 degrees north, so mid-latitudes. This is the input sanding that I'm using. This is the classic Weismann and Klemp sanding, but we modified the sanding adding a thermal inversion of 4 Kelvin. This is because I have radiation in my simulation. And with the radiation, with the solar radiation, the Weismann and Klemp profile becomes unstable very quickly. In just 1-2 hours, we have radiation convection everywhere in the simulation. Well, so we needed to add this thermal inversion. And the wind profile is taken from Markowski and Ozek 2011. The general idea, the theoretical framework to choose this type of profile is explained by this paper of Kerry Emanuel to create high CAPE. So we know that to have high CAPE, typically we start with a dry elevated mixer layer, then there is the advection of some moist, cool air mass close to the ground, and this is the initialization sanding that I showed you before. And in the afternoon, I'm expecting this profile. So with the solar radiation, there is the mixing that is working the boundary layer, and this is increasing the temperature, slightly decreasing the moisture, and I have this profile with high CAPE. And indeed, this is the profile that I have at 4 p.m. in my simulation, so I'm happy about that because it's something realistic. And I have a surface-based CAPE of 2,700 joule per kilograms, which is a pretty high value of CAPE. It's not extreme, so it's something realistic but not extreme, with an LCL height of 1 kilometer. This is an example of the simulation feature. The gray shading in the plot on the right is, maybe I can show, yes, this one is the city. In this case, it's a pretty small city. And I'm triggering the storm at 4 p.m. The storm is going to split after 40 minutes. And after 2 hours, the storm, the right mover supercell is going over my city. And then it continues to go toward the east. We are using an ensemble approach. So with the in particular, we are using the stochastic kinetic energy backscatter scheme, SKEBS. So for each numerical experiment, we have a control run plus 10 ensemble members. And we are tracking the right mover supercells with the spout tracking algorithm developed by Terry and Rose of 2014. And on the right, you have an example of the trajectories of this right mover supercell and the spread of the trajectories due to the ensemble that we are creating. And then I am extracting the storm diagnostic following the storms. And I'm using a radius of 8K around the center of the storm. And then I'm taking, for example, the vertical velocity at different pressure levels, vertical vorticity, updraft elasticity, what do you want, basically. It's not everything, because we want also to understand if the storm is modified, if there are differences in the effect of the city on the storm, if it is upwind of the city or downwind of the city or over the city. To do that, we are using time-defined algorithm, I will say. So my zero is when the storm is over the city, and then I'm considering 40 minutes windows. So for example, for the city region is minus 20 minutes plus 20 minutes, okay? And then I have the downwind region, other 40 minutes, sorry, in the future, and 40 minutes in the past with respect to the zero of the city. And I'm doing an average of the extracted variables in these 40 minutes windows. The city is parameterized with the building effect parametrization, the building energy models. These are the state of the art for urban parametrization and for mesoscale modeling, at least. They are pretty complicated models, so they take into account a lot of phenomena that occurs in the city. So for example, the shadows of the buildings, the wake generated by the buildings, also the exchange of temperature and moisture between rooms and the outdoors. So they are pretty sophisticated. And I would like to acknowledge the work of Andrea Zonato that coupled these two models with idealized work and permitted to do this type of simulation. These models need some morphological parameters to be run, and I'm using as a source for these parameters the Globus dataset, and there is Harsh Kamath that is visiting RAL now, and he published last year this very, very nice database that I really encourage you to use if you're doing some urban studies, because there is basically everything you need. And this is an example. On the left here, you have the Milan urban fraction. On the right, you have the Oklahoma city urban fraction from the Globus dataset. What I did is basically I did an average of the urban parameters inside the red boxes, for example, the Milan and Oklahoma city ones. Why I'm doing an average? Because in my idealized city is uniform. I don't have different heights of the buildings. Everything is uniform because I want to control everything. I would like to understand what is the effect of a specific parameter of the city to my storm. And to do that, I need some morphological parameters that are realistic. So I'm using this data set to have some realistic values of those parameters to initialize my simulation. And those parameters are, for example, the building height, the street width, the building width. You can then obtain, for example, the planar refraction, these other parameters that are, for example, this one is describing how much dense are the buildings in your city. And from one city to the other, you can have pretty different values of these morphological parameters, and probably it's also your experience that one city, New York, is different from Oklahoma City, for example. And so this is an argument that makes sense to explore different parameters and see how the storm is sensitive to those. Okay, I think it's everything for the method, and now we can jump in the results. This was a nice supercell in Bologna, so also in Italy we have nice supercells, even if I have to say here in the US are better, but you say something. Okay, so first of all, the sensitivity of the storm on the city size. So I'm using, I'm fixing basically the urban fraction, building height, building width, and street width as the values of Milan, the average of Milan. Why Milan, you're asking? Well, probably because I'm from northern Italy, but also because these values are pretty common of Western cities, so it's something realistic. What I'm changing in these numerical experiments is the city size, from the urban case to the case of a 30K of diameter. For each experiment, I remember you, there is one control run plus 10 ensemble members. This is one of the first results. This is the updraft helicity over the city versus in function of the city size. So on the x-axis, you have the city diameter. On the y-axis, you have updraft helicity, which is normalized with respect to the no-urban case, because I want to understand what is the changes of the storm with respect to the no-urban case. Each dot here is the result of a simulation. So for each diameter, I have 11 dots, 10 ensemble members plus the control run. And I'm connecting with a line the simulations with the same seed because they are not independent otherwise. And then I'm doing a linear fit among the simulations with the same seed. So you have 11 linear fits, and then I'm doing an average on those slopes, and the red line is that average. And the red shading is the confidence interval of 5 to 95% obtained with a bootstrap algorithm with 1,000 of iterations. I think is everything to explain this plot. And okay, so what you can see is pretty clear. I think there is a weakening of updraft helicity in function of the diameter of the city. It's not true for every ensemble members. For example, this ensemble member is increasing, but the overall behavior is a decreasing of updraft helicity. And this trend is consistent across all the variables that I analyzed and also for all the regions that I consider, so the upwind, city, and downwind region. In this slide, you can see some of the variables, and the minus sign is, these are the slopes, and so the minus sign is telling you that there is a weakening trend of updraft helicity, no, of these variables, not only updraft helicity, with respect to the diameter of the city. Bolded values are those that are statistically significant. Then we replicated the experiment, changing the urban fraction. Instead of using urban fraction 0.6, now I'm urban fraction 1. What is the difference? With urban fraction 0.6, I have gardens, parks in my city. With urban fraction 1, I have only buildings, streets, so everything that is developed. And the experiment, for the rest, is absolutely the same. And these are the results. So also in this case, I have a weakening of my proxies for the supercell. It's even stronger in this case. But as you can see, I tried also a quadratic fit. I think it's the only case that I obtain a statistically significant quadratic fit for the samples that I'm using, because until 10, 15K of diameter of the city, there is not a strong signal of weakening of the storm. While after that, the signal is much stronger, so the storm is really weakening pretty a lot. It's about 30%, as you can say, the weakening. So, and yeah, I think is everything for this slide. Okay. Then, at this point, okay, there is the suspicion that maybe urban fraction is another important parameter that will be worth it to investigate. So now the city size is fixed at 20K of diameter. What I'm changing is the urban fraction from 0.4 to 1. And this is the result. In this case, there is not a strong signal of weakening of the storm. As you can see from the confidence interval, this is pretty wide, so there is a lot of uncertainty. Indeed, for the city region, the downwind region, there is not, they are not statistically significant. While for the upwind region, there are some variables that are statistically significant. So higher urban fraction is contributing maybe to the weakening of the supercell, but is not the parameter that accounts the most to the weakening. New experiment, building height. So what now I have again, the city size fixed at 20K, the urban fraction is the same as before at the beginning, so 0.6. What I'm changing is the building height from 10 meters to 60 meters. And this is the result. So in this case, I have something different. I have an intensification of my storm with higher buildings. And this is true in particular for the upper levels variables that are describing my storm. While, for example, for the low-level mesocyclone, I have a weakening in this case over the city. So it's not really true for every variables or every layer of my storm, but at least for the upper levels, it's true. Last experiment, I think, and this is the sensitivity on the building density. So now again, the building height is fixed at 20 meters, and what I'm changing is the width of the street. So the building width is kept constant at 20 meters, and the street width is changing from 100 meters to 11 meters. Okay, so from a very sparse city to a very compact one. And this is the result. It looks like similar to the urban fraction one. So there is a weakening of the storm, but it's not really strong. It's not statistically significant, as you can see, with the exception of some variables in the upwind region. While in the downwind region, there is not a clear trend. So sometimes there is an intensification, sometimes a weakening, but it's not statistically significant. I did another experiment, because in BPBM model, you can also add vegetation in your roof. So you can do an experiment with green roofs. I'm using, so as I took the experiment with the biggest city, the 30K of diameter city, with urban fraction 1, so the most extreme city that I considered, and then I added vegetation. Now I'm showing you the track of updraft helicity. Of course, again, is the ensemble mean. So on the left now you have the track of updraft helicity in the no urban case, where you can really, you can see the right mover supercell very well. This was the experiment with the 30K of diameter of the city, so you can also visually see now the weakening of the storm as it goes over the city. And this is a statistically significant weakening. And this is the situation if I had green roofs in my city. There is an intensification, pretty significant intensification with respect to the 30K diameter city. But yeah, there is not a statistically significant modification with respect to the no-urban case. So adding green roofs looks like I'm maintaining the intensity of the initial storm. And this, I wasn't expecting something so strong. So it's really a different behavior of the storm, just adding green roofs in the simulation. Okay, so now at this point, I'm sure that you are wondering why is the storm weakened by the city? You have this question, I had this. And so now this permits me to go to discuss the pre-storm environment and the sensitivity of the pre-storm environment to the urban morphological parameters. Okay, starting from surface variables, so this is temperature at 2 meters, specific humidity, and also the wind speed at 10 meters. This is the difference between the ensemble mean with the 30K diameter city and the no-urban case. So the most extreme city that I considered and the no-urban case. You can clearly see the urbanish island over the city, but also the color shading is the temperature. The contour lines are specific humidity. You can see that the urbanish island is propagating also downstream, and you can see that also the blue contours lines are specific humidity that is lower in the urban case than in the no-urban case. So you can see a strong correlation between higher temperature and lower moisture. This is a trace of the urban air mass. And finally, also the wind. You can see this strong convergence downwind of the city. This is quite impressive, I would say. While over the city, there is a weakening of the wind speed. And the wind convergence is in correspondence of a minimum of pressure. This is mean sea level pressure, and you can see it is minimum that is displaced with respect to the city. It's located here, the center of the minimum. And the wind in this case is the one of the urban case. So you can see the really actual wind, and you can see the bifurcation of the flow around the city. So one may wonder, is the pressure minimum thermodynamically or dynamically induced? We know that we can divide the pressure perturbations in buoyancy pressure perturbation and dynamic pressure perturbation, and we can compute both of them. And we did it, and this is the result. And as you can see, the buoyancy pressure perturbation, which is this one in the center, is the one that is accounting the most to the pressure minimum on the left, while dynamic pressure perturbations has a very marginal effect. And to support this conclusion, there is the green roof experiment that is helping me, because this was the plot that I showed you a few slides ago, and this is the same plot with the green roofs experiment. As you can see, there is no urban niche island, there is no modification of moisture, and also there is no wind convergence downwind of the city, while I still have the weakening of the wind over the city, because I have the building, so there is the effect of the drag, of higher drag over the city. And this is the pressure field in this case. So I don't have the urban niche island, and also I don't have the pressure minimum. So this is a proof that this pressure minimum on the left is caused by the urban niche island. This pressure minimum is causing also a completely different pattern on storm relative elasticity. This was a pretty nice result, I think. On the left, you have the no green roof experiment, and you can see that south of the convergence line here, there is a weakening of SRH, and this is because the wind is more from the south, so there is less veering of the wind. While north of the convergence line, there is a more easterly component of the wind, and this is causing higher values of SRH. Without the pressure minimum on the right, with the green roof experiment, there is basically no significant modification, and there is only a slightly higher values of SRH over the city, but with respect to the modifications caused by the urban niche island and the pressure minimum induced by the urban niche island, I will say that these are negligible. Regarding CAPE, now I'm showing you the sensitivity of CAPE on the different morphological parameters of the city. So first of all, on the left, the sensitivity on the city size. There is a drastic reduction of CAPE. We are talking about 1,000 jar per kilograms over the city and in this wake downwind of the city. I remember you that is an extreme scenario of a big city with urban fraction 1. So it's not, I think there is no cities in the world with such a big size and such big high urban fraction. But it's just to show you how much can influence the urban land use, the environment. This instead is the sensitivity to the building height. So it is the difference between a simulation with height of 60 meters of the buildings minus the simulation, not a simulation, ensemble of with a building height of 10 meters. So with higher buildings, you have higher CAPE, which is pretty weird. I wasn't expecting that. I will come back on this point later. On the right, you have the building density. In this case, there is not really strong modification of CAPE. I would like to connect to the results that I showed you at the beginning regarding the supercell sensitivity on those morphological parameters. Because if you remember, there was a pretty strong sensitivity on the city size, and in particular, there was a strong weakening of the supercell intensity, and this is probably caused by these much lower values of CAPE. While if you remember in the building height case, I had an intensification of the storm, and in this case, I have higher CAPE. So this is probably what is driving my intensification of the storm. And in the building density case, I didn't have a statistically significant trend, and indeed there is not a significant difference in the CAPE field. And finally, on the right, we have the urban fraction, where I have again a pretty strong signal. With a higher urban fraction, I have lower values of CAPE over the city and downwind of it. Regarding the vertical velocities at 950 hectopascals, there is something else which is interesting, I think. So first of all, you can clearly see the wind convergence downwind of the city that is causing these enhanced vertical velocities. In the case of the building height, you have a weaker wind convergence here, and this is because the pressure minimum in this case is weaker. I think I have a slide after that about that. The only effect of the building height in intensifying the vertical velocities can be seen here. I don't know if, yeah, you can see it. In the upwind side of the city, there is slightly higher values of vertical velocities. So the effect of building height, I will say, is not really important to cause stronger storm, because at least regarding the vertical velocities induced directly by the building, there is an effect on the urban edge island is inducing a pressure minimum, which is inducing pretty strong vertical velocities, but the buildings inside itself are not causing really an effect. Regarding the building density and the urban fraction, there is an intensification of vertical velocities downwind of the city. I remember you, this is the difference. For example, the building density is the difference between a compact city minus a sparse city. And the urban fraction is the difference between an ensemble with urban fraction 1 minus urban fraction 0.4. And there is a sensitivity, but is not so strong. There is an intensification of these vertical velocities, but is less strong than in this case. So the city size is the parameter which is accounting the most to create a modification of my pre-storm environment. This is so the differences of some surface variables. So the first line is the mean sea level pressure. The second line is temperature, moisture, and wind. And these two plots about the city size, we already discussed them a few slides ago. Regarding the building height, you can see that there is lower temperature in the city if you have higher buildings with respect to the scenario with smaller buildings. We think that is due to the shadows of the buildings. And so in the canyons, we have less solar radiation, basically, and so the temperature is slightly lower. And this lower temperature is causing less mixing, and this less mixing is making that the moisture in the canyons is trapped, basically. And so I have also slightly higher values of moisture with higher buildings with respect to the simulations with small buildings. And this is what is causing these higher values of CAPE that I observed in the previous slides. And so the higher moisture is causing higher CAPE, while the lower temperature is causing a less pronounced pressure minimum downwind of the city. Regarding building density and urban fraction, there is a similar pattern in the sense that with a more compact city, you have slightly higher temperature and so slightly more pronounced pressure minimum. With a higher urban fraction, you have a stronger urban edge island and then a slightly stronger pressure minimum. So this is pretty, I would say, consistent with the previous results. Okay, why I focus so much on this pressure minimum and on this wind convergence? Because there was in the case with a big city with urban fraction 1, there were most of the ensemble members that developed a new supercell. So from one side, I have that the supercell that I'm triggering with the thermal bubble, so artificially, is, okay, now it's starting again here. This storm is going to be killed, to be suppressed by the environment that I described before, so the dryness that is caused by the city. But then along the convergence line, which is these red contours here, there is some convection that is popping up and is triggered, and because the environment is favorable for supercell, this is going to be a new right mover supercell. So from one side, I'm suppressing the initial storm, but from the other side, I'm generating a new supercell downwind of the city. And yeah, maybe you would like to ask, when have I the self-produced supercell? So this is the tracks of updraft helicity, is the ensemble mean. On the left, you have the urban case. This is the case with a 20K diameter city, and you can see the supercell dissipation, but there is nothing here. While if you look to the average updraft helicity with a 30K diameter city, you have this new track of updraft helicity, and this is the new supercell generated by the city. While on the other side, you have the dissipation of the first supercell. I tried to see if there is something similar also in the other experiments that I did, but the answer was not. I have only in this case, basically, the new supercell. While for the other experiment, there isn't. And I think the reason is that this is the case where the urban H island is stronger, and so the pressure minimum is stronger, and the wind convergence is stronger enough to trigger the new convection. In these other cases, this is not true. Okay. At this point, maybe you may ask, okay, beautiful, but there is some observational evidence because this is only in the model space, so you can trust the results or you cannot, so it's absolutely fair. But luckily for me, yes, there is some observational evidence, and there are two papers that was published pretty recently, one for Europe, for Berlin, the other one for some Great Plains cities. Both of them are radar-based climatologies, so pretty solid studies. For example, the first one for Berlin, they found that the storms hitting Berlin were more frequently weakened than intensified. And the other paper for Great Plains cities, they also find lower reflectivity values downwind of the city with respect to the upwind region. So there is also for Great Plains cities an indication for a weakening of approaching storm toward big cities. But the second paper, they try to replicate the analysis for a subset of, they called urban favorable environment. And they excluded supercell situations for this subset. And doing that, they found an opposite result. So they found an intensification of downwind convective precipitation in this case. So it looks like that there is a sensitivity on the results on the environment that you are considering. With different environment, you can have opposite result, basically. So from one side, this is what I obtain with an environment favorable for supercells. So if you have a supercell that is going toward a city, and in the city there is a dry urban air mass, then your supercell may be suppressed. But the urban H island is causing a pressure minimum, and this pressure minimum is inducing some wind convergence that can induce a new supercell downwind of the city, or at least in the nearby close to this pressure minimum. This is one scenario, but the other scenario, if you have a weak flow, if you don't have an environment favorable for supercells, then your urban H island is exactly over the city, the pressure minimum is over the city, the wind convergence is over the city, or slightly maybe downwind, but maybe is basically over the city, and then there is the triggering of new convection that propagates downstream of the city, and this is basically what was found in the studies that I showed you at the beginning of my talk. So my results are not opposite with respect to what I showed at the beginning. It's just, I'm enlarging the environmental space of this phenomena, and with this pretty curious bifurcation. From one case, you can have a suppression of the supercell and then an initiation of a new supercell in the environment that I studied. Also a summary about the pre-storm environment. So coming back to the initial sketch, regarding the thermodynamics, I observed an intensification, higher temperature, which is quite well understood, lower moisture over the city, but then also lower CAPE. So moisture is winning. The decreasing of moisture is driving the decreasing of CAPE. Regarding the kinematics, I have less intense surface winds over the city, but regarding the wind shear, it's not really clear in the sense that you can have an intensification of wind shear because of that, but if you have a pressure minimum, this pressure minimum is changing everything, and so you can have a decreasing of wind shear because of the location of this pressure minimum induced by the city. Regarding trigger, it is basically what was already been observed. So you have wind convergences of the city and then with vertical velocities that can trigger new storms. Even if these vertical velocities are not modifying the behavior of an already triggered storm, are just causing new convection eventually. Some concluding remarks. Supercell storms are not immune from urban modifications. Secondly, green mitigation strategies in cities, for example, green roofs, increase the urban moisture, potentially favoring more severe storms. I will say that, okay, you can have more severe storms with respect to the city without green roofs. But with respect to the rural area, you don't have an even more intense storm. You just maintain the same intensity of the storm. So I wouldn't say that having green mitigation strategies in cities is a problem because of these new storms. Okay, it's just in the best case, in the worst case scenario, you have the same storm that you have in the rural area in the nearby. The point that was surprising for me is that supercells are extremely sensitive to the land use, especially to the moisture exchanges between the ground, vegetation, and atmospheric boundary layer. I think this can have an implication also for forecasting application, because from one side, you need very good parameterization of these exchange processes between land use and the boundary layer, but also you need very updated values of the land use in every moment, because from one week to the other, you can have different pattern of vegetation because of the evolution of vegetation during the year, but also of rain, drought, etc. So this is a point that must be, I think, keep in mind. And the last point that was also surprising for me is that the height of the building is not influencing really the kinematics on the environment. So vertical velocities and SRH are weakly influenced by the building height. But there is an influence on the amount of moisture on cape because of this moisture that is trapped in the canyons. And I will end with a special thanks to Chris and Stefano for hosting me this month. And it was a pleasure to work with them, but also we had a great time hiking in the Rockies and doing track repeats and storm chasing also recently. So thank you very much, and thank you all of you for attending this seminar, and I'd be glad to answer your questions.
All right, thank you for that great talk. We'll take questions in the room and online. Anyone in the room first?
Thanks for the talk. I'm just curious about what's on your radar next. What kind of experiments are you thinking about doing to take the analysis further, and what kind of questions you want to ask?
So try to do an observational study about to confirm or reject this result, you mean? I don't know. I think the work of Kingfield was this one. They used the next-rate data, and I think it is a pretty good study. Maybe they consider just 4 or 5 cities, so you can try to consider other cities. But yeah, this can be a starting point, a good starting point. And for other, maybe in Europe, I would like to extend this analysis to other cities in Europe, and also would be interesting to cities in Asia, for example, because there are quite a lot of studies that found a strong sensitivity of storms to urban land use in Asia. So that could be another point. But yeah, the Kingfield work, I think, is pretty solid already. So.
Thanks for the talk. I was just wondering if you have considered the effects of aerosol emissions from...
This is another freedom that should be considered. I completely agree. And I think there is at least one paper in Houston, if I remember well, that they found a strong sensitivity on urban aerosols on the storm. So this can be another point that could be investigated with Wolfram, for example.
Yeah, I think you use the Morrison scheme, so you can maybe change droplet number concentrations or something to see at least some impacts or something like that.
I can add a new experiment with that. Thank you for this advice.
Do you have a question online from Tayun Kang? Thank you for your interesting talk. I would like to know the impacts of anthropogenic heat on the formation and simulation of supercells.
I think that the urban inch island is a consequence of anthropogenic heat. So I will say that is pretty strong in the sense that is what is causing the new supercell downwind of the city. And but on the storm itself at the beginning, the moisture was the most important factor, which is not strictly related to anthropogenic heat, but is more related to the lack of vegetation in your city.
Way back when I worked on this problem, we sometimes differentiated between anthropogenic heat and the sensible heat from the buildings, the storage,
You mean cars, for example?
cars,
the
air
engine?
conditionings, any kind of exhaust.
Okay, okay, I get you. I don't know. I don't know.
Those are included in the parameterization of Martini. They consider the heat
From
AC or
yeah, AC, sure, for sure. Traffic, I don't know. Actually, I'm not sure. Probably not. Not.
Yeah, I recall it was relatively small, typically even for large cities, compared to the sensible heat release from the heat storage.
Makes sense.
Anyone else? Otherwise, we can wrap it up a little early, but I want to just let you know that Francesco will be around through the end of June, so please do stop by and talk to him about science and weather, and he's a delight to speak to. And again, thank you all for being here today. Let's give a round of applause for our speaker again.